Hi, I'm Mr. Miller, and this is a lesson on solving exponential equations. So if you take a look here, I've got a number of steps that can be used to solve exponential equations. And I've got several examples that I'm planning to do here. But I decided to add an extra example here. So if you're looking at this handout that I've given you and it doesn't have this extra example up here, I would encourage you to write this one down. And the reason I've got this example here is because sometimes in solving exponential equations, and by the way, we're talking about algebraic solutions because we've already looked at how to solve this using a graph. If you're solving algebraically, sometimes you'll want to start by isolating the exponential part of the equation. So the exponential part is the 3 to the x. You notice it's multiplied by a factor of 2 here. So sometimes you want to take a first step of dividing both sides of the equation by a constant in order to isolate that exponential part. So I'm going to do that right now. Divide both sides of this first equation by 2. It gives me 3 to the x equals 27. And at this point, we can take a look at step 2, which is to rewrite both sides of the equation using a common base. So 3 to the x is one thing, and it currently has a base of 3. If you look at 27, if you know your powers of 3 well, you know that 27 is a power of 3, so you can rewrite the right side as 3 cubed. And at this point, you look at this step, it says simplify both sides of the equation. There isn't really any more simplifying that you need to do. It becomes obvious at this point that since the base is the same on both sides of the equation, that the exponents also have to be the same. And so step 4, where you equate the exponents, is what we do next, and of course that's the solution of the equation. Sometimes there's more work to be done here in step 5 to solve the resulting equation, but in this case we are done. Now I want to say a word or two about checking, because obviously this might seem pretty simple, straightforward. I think I've got it, cool. But you want to do a check sometimes. So there's a number of ways that you can do checks. So one way that you can do a check is to go back to your other method of doing a graphical method. So if I go in here and I punch in y equals 2 times 3 to the x, and I graph that, and then I graph y equals 54. Now, at the moment, I can't see where those two intersect. Of course, I know from having solved this already that they intersect at x equals 3, but I can see that at x equals 3, both graphs are way off the grid here. So I need to do a little bit of zooming out to find that. And so now I can see where they cross, and it's here at 3 for the x-coordinate, 54 for the y-coordinate. So of course the solution of the equation is the x-coordinate of this point of intersection, and so it's x equals 3. Now if you don't like the way this looks, you can always play around with projector mode and reverse contrast and all that jazz, but I'm just going to leave it like this for now. And that's one way of doing a check. Of course, another way of doing a check is to simply evaluate the expression 2 times 3 to the exponent of 3, and realizing that's 54, that matches the right hand side. So this is another way for you to do a check. And hey, if you're a hockey player, then you probably like to check. Anyways. All right. So let's go back to normal there. We'll head back over here to the examples and take a look at the next one, where we've got 8 to the 3x minus 2 equals 16 to the x plus 1. So if I take a look at my step 1, it says, if necessary, divide both sides of the equation by a constant, which could be used to isolate an exponential part. Well, we've got two different bases, two different exponential functions, and they're not multiplied by anything else, so it doesn't look like I need to divide both sides of the equation by anything in order to proceed. So what I want to do is I want to go to step 2 now, and I want to rewrite both sides of the equation using a common base. Now, if you know your powers of 2, you'd probably recognize that 8 is a power of 2 and 16 is also a power of 2. So I'm going to rewrite both sides like this. So I rewrite the left, the 8, as 2 to the power 3, and I rewrite the 16 as 2 to the 4. And now I can go on to step 3, where it says to simplify both sides of the equation. So to simplify this, what I'm going to have to do is use a law of exponents. So when you have 2 to the power of something to the power of something else, what you do is you multiply those two exponents. So I'm going to do 3 times x minus 2. And that gives me 9x minus 6. Now, notice you have to be careful here because it's 3 times 3x, which is 9x, and you also have to do 3 times negative 2, which gives you negative 6. And I'm going to perform a similar step on the right side. I'm going to multiply the 4 times the x plus 1, and notice I'm doing 4 times x is 4x, and I'm also doing 4 times 1, which is 4. And at this point, you should recognize we have 2 as the base, 2 as the base. Those two parts are equal. Therefore, the exponents must be equal to each other. So step 4 is a natural step to say, let's equate the exponents now. So the 9x minus 6 must be equal to the 4x plus 4. And at this point, kind of a bit of a contrast from the last one, when we equated the exponents, we were done. Here we've equated the exponents, and of course there's still an equation that needs to be solved here. It's a linear equation. This is the kind of equation that you should have been able to solve by the time you were in maybe grade 8, but definitely grade 9. And so what we want to do here is we want to move all the variable terms to one side, the constant terms to the other side of the equation, and divide by the coefficient of the variable. So I'm going to subtract 4x from both sides. That gives me 5x minus 6 equals 4. I move the constant terms to the other side of the equation, so I'm going to add 6 to both sides. It gives me 5x equals 10. And I'm going to divide both sides by the coefficient of the variable, and that gives me x equals 2. And this is the solution of the equation. Now, I want to talk again about checking because it is good to make sure that you've got the right answer. And so let's take a look at plus. This is maths class. Mathematics is plural. There's more than one method. This is just an algebraic method, and we should recognize that there is another way to get a solution here, which is graphical. So I'm going to graph 8 to the 3x minus 2. So I go in here and I put in y equals 8 to the 3x minus 2. Oh, now it booted me out of the exponent part of it. I still wanted to be, oh dear. Okay, so I guess what I need to do here is I need to put this in brackets. So if I put this in brackets, the 3x minus 2, that whole thing needs to be the exponent. Okay, fantastic. So now I'm going to take a look at the other side. It was 16 to the x plus 1. So I'm going to go y equals 16 to the x. Now I bet it's going to boot me out of the exponent. Yeah, it does. So I need to, if you're doing this in Desmos, take a look, put it in brackets, because otherwise you may not get the function that you're looking for. So I want to equate these two things, and I can see that we don't have a solution here. I already know that my solution should be at x equals 2, but at x equals 2, both of these graphs are off the grid. So it looks like what I need to do is, and I can just pull this down like this. It's a little bit easier on a mobile device where you can just pinch to zoom out. But anyway, so I'm going to do my zooming out here, and at some point, holy cats and dogs, I think I'm going to have to go ahead and just go from -5 to 5 for x, and y can go from, like, I don't know, -100 up to maybe 1,000. Do we see where they cross? Oh my gosh, no we don't. So I'm going to have to go a little bit higher than this. How about 10,000? That's probably going to do it. Yeah, okay, now I can see where they cross. There it is. X equals 2, y equals 4,096. So this is one way to check what the solution is. The other way to check if your solution is correct is to evaluate this expression on the left side. So and by the way, don't forget that you can also use the keypad even if you are on a computer, as I am right now. So I can go 8 to the exponent 3 times, oh, and see, it's kicked, I can tell it's kicked me out of that exponent part. So I need to put that exponent in brackets. So I've got 3 times 2 minus 2, and there we've got 4096. And that was the y value that we saw here. So it's nice to know where that's coming from. And so the other expression that I can evaluate is 16, and it's going to be to the exponent, and I'm going to put the exponent in brackets, and I'm going to go 2 plus 1 and close the brackets, and it's also 4096. So obviously having the same value here for the left-hand side of the equation, the right-hand side of the equation, confirms that using x equals 2, this is the solution that satisfies the equation. So whether you're doing it graphically or if you're just evaluating both sides of the equation with the solution that you think is correct, either of those ways as a check would be good for you. Of course, on a test, if you're not allowed to use a graphic calculator, then this is the one that you'd want to use. Okay, cool. So I'm going to clear these out here, make some room for other work as we get to it. We'll slide across here and we'll take a look at the next example. So we've got 27 to the x plus 3 equals 1/9 to the 2x minus 5. And so what you'll notice is that each one of these examples has something a little bit different to offer. The first example, what I really wanted to point out was sometimes it's necessary to divide both sides of the equation by a constant. What I wanted to show with this is sometimes you have to use a law of exponents to simplify the expression, and other times you're dealing with a situation where you're looking at these two bases currently and you're saying, oh man, I don't know if they have a common base here. Well, I know 27 is like 3 cubed from doing this before, and then you say 1/9. Oh, wait a minute. Yeah, that's 3 to the minus 2. So dealing with negative exponents is something that you should be able to handle. And so that's going to give us our first step. Notice that we don't need to divide both sides of the equation by a constant for this example. We can go straight to rewriting both sides of this equation with a common base, and I'm going to use 3. So as I mentioned, the 3 cubed is 27, and 1/9 is 3 to the minus 2. So don't forget about negative exponents, that 3 to the minus anything is going to be 1 over 3 to that same exponent, but the positive version, the opposite. So we get a reciprocal of 3, 1 over 3, and then square it. That's 1/9. Now from here, I do a very similar step to what I had done in the next step here. I'm simplifying both sides of the equation, and I'm using a law of exponents. I'm going to do 3 times x plus 3, so that's 3x plus 9. And on the other side, I'm doing negative 2 times 2x minus 5, so I get negative 4x plus 10. At this point, it's pretty obvious, since the bases are the same, that we want to equate these two exponents with each other. And once we've done that, we can solve the resulting equation, which again is a linear equation at this point. So variables on one side, constant terms on the other side, divide by the coefficient of the variable. Let's take a look. I'm going to add 4x to both sides. I get 7x plus 9 equals 10. I'm going to move the constant term of 9 to the other side. So minus 9 from both sides, I get 7x equals 1. I divide both sides by 7, and I get x equals 1/7. And so now, again, this is something that you could go ahead and do a check. You could do it graphically. You could just do it by evaluating the left-hand side of this equation, substituting in x equals 1/7, and substituting into the right-hand side x equals 1/7. Evaluate those two sides and verify that you get the same numerical value. So I'm not going to demonstrate that because I think you should have the idea by now. Let's take a look at another example that gives a little bit more complexity. What if we're dividing two different powers, and how do we deal with that scenario? So what you should recognize in the 8 and the 16 and the 32 is that they're all powers of 2. 8 is 2 cubed, 16 is 2 to the 4, and 32 is 2 to the 5. So from here, what I need to do is use my laws of exponents to simplify both sides of the equation. So I'm going to do as I did before. I'm going to do 3 times x plus 6. So that gives me 3x plus 18. I'm going to do 4 times 2x minus 1. That gives me 8x minus 4. And I'm going to do 5 times 3x minus 4, which is 15x minus 20. So now at this point, we've got an extra step from compared to previous examples. It's how do we combine these things together? So when you have a power divided by another power and they've got the same base, there's a law of exponents that says we can take this exponent and subtract that exponent. So that's what I'm going to do. I'm going to take the 3x plus 18 and I'm going to subtract the 8x minus 4. On the other side, there isn't any work to do. It's already simplified. So what I need to do now is just do 3x take away 8x, which would give us negative 5x, and then 18 take away negative 4. So just be careful with your work on integers there. Otherwise, I'm going to have to send you back to grade 8 math. Just kidding, I can't really do that. Anyways, it would be negative 5x plus 22 is the exponent on the left. On the right, we don't have anything changed. And now at this point it does become obvious because we have the same base on both sides, so therefore the exponents must equate to each other. And this resultant equation is a linear equation, so I'm going to isolate the x. So I'm going to move all the x terms to one side, all the constant terms to the other side, and then divide both sides by the coefficient of the variable. So I'm going to add 5x to both sides. It gives me 20x on the left. And now I'm going to add 20 to both sides. It gives me 42 on the other side, on the left side. And dividing both sides by the coefficient of the variable 20, I get a single x is 21 over 10 as an improper fraction reduced in lowest terms. You could leave it as 42 over 20, but it's not simplified. So 21 over 10 is the simplified version as an improper fraction. As a mixed fraction, you'd say it's 2 1/10, 2.1 in decimal form. All of these are exact and they're equivalent in value, so whichever one you prefer is okay with me. And now we've got part D, and so we've got another little twist here with the square root. And so you should know what the square root is as an exponent. And so that's coming up now. So 125, this is 5 cubed. The 5 is 5 to the 1. The square root of 5 is 5 to the 1/2. So remember that. It's something that you may have learned about grade 10 math, that square roots are equivalent to doing to the exponent 1/2. And now we can simplify both sides of the equation. So I'm going to multiply the 3 and the x, that's 3x. When I have two powers with the same base that I'm multiplying, I add these two exponents together. So it's 1 plus 1/2, or in other words, 1 1/2. And now, since we have the same base on both sides of the equation, we can equate those two exponents. So the 3x is equal to 1 1/2. And now I can divide both sides by the coefficient of the variable and get x equals to 1/2. So if you didn't realize that 1 1/2 is 1/2 of 3, well, there you go. It is. And you can go ahead and check that if you want, and you should find that it works out. So let's now move on to some application type examples. So I'm going to read this first paragraph here about half-life. The half-life of a substance is the amount of time it takes for the substance to reduce to half of its initial quantity, usually mass. The most direct applications are in physics, so we're talking about radioactive decay. However, the math behind exponential growth and decay can be applied in a number of other fields. So here's an example where we've got at noon, this is a start time, we've got 100 grams of a radioactive substance, and we know that its half-life is 3 hours. So first of all, we're going to write an exponential function that models the amount of radioactive substance that's left t hours after that start time of noon. So here's how I'd write that equation, that function. So A, the amount I have in grams, is starting at 100, and we're multiplying by 1/2 because we're talking about half-life. We get half of the amount every 3 hours. So when t gets to 3, that's going to be a half to the 1. When t gets to 6, that's going to be a half to the 2, and so on. So hopefully that makes sense why we're dividing by the 3. And again, we're dividing by the half-life. And now the question is, at what time will there be 25 grams left? So we want to equate the 100 times a half to the t over 3 to 25. And now we've got an equation kind of like that very first one that we did. And with that very first one that we did in this video, to solve it, we divided both sides of the equation by a constant in order to isolate the exponential part. So I'm going to divide both sides by 100 first and get a half to the t over 3 equals 1/4. Now at this point it's kind of looking pretty obvious where we're going from here. This t over 3 must be 2, right? But I'm going to follow through the steps as we did them before. So I'm going to write the 1/4 as a half squared. And then I'm going to say, okay, now I can see they have the same base, so therefore the exponents must be the same. I'm going to equate those two exponents, and I'm going to solve the resulting equation by multiplying both sides by 3, and I get t equals 6, and this is time, so it's 6 hours. So to answer the question, the 6 is the number of hours after noon. Remember, this is the start time. So 6 hours after noon would be 6 p.m. At 6 p.m., there will be 25 grams of the radioactive substance left. A couple more application questions and then we are done. So let's look at example 3. A population of rabbits starts at 200 and has reached 1,600 in 15 months. We want to find the doubling time for this population of rabbits. So we're going to write an exponential function to model the situation. So it's an initial population of 200 and we're multiplying by 2 because the population is doubling. And we're raising it to the t over capital T2. This capital T2 is the symbol that I'm using for doubling time. Now this is kind of strange that we've got two variables here, but hang on one second and you'll see how we use this. So if we substitute in t equals 15, the reason 15 is because we're looking at time 15 months. Here's the expression that we get in the function. And we know that the value gets up to 1,600 by that point. So now we have an exponential equation to solve. And it does have an exponent that's looking a little bit different, but I think you're going to find it's not too hard to solve this. So I'm going to start in the same way that I did just the last example. I'm going to divide both sides of this equation by a constant. So I'm dividing both sides by 200. The reason I want to do this is because it allows me to isolate this exponential part. And you should be able to recognize at this point that 8 is a power of 2, and it's 2 cubed. Now, because we have the same base on both sides, we can equate the two exponents. So the 15 over doubling time is 3. I like to write the 3 as 3 over 1. That way, some people like this way, to cross multiply. 1 times 15 equals 3 times T2. Right? Divide both sides of the equation by 3, you get T2 equals 5 months. So this is the doubling time, 5 months for the population to double. And the final example here we have, if a population of rabbits starts at 150 and doubles every 7 months, then how long will it take for the population of rabbits to reach 4,800? So again, we're starting with the initial population. We're talking about doubling, so we've got 2 as the base. The exponent is t over 7, and the reason we're dividing by 7 is because that's the doubling time. What we want to do is figure out what is the time required for the population to reach 4,800. So we're equating the expression to 4,800. Again, I want to isolate this exponential function here, so I'm going to divide both sides by 150. And I get 32 on the right. 32 is the power of 2. You should recognize that. It's 2 to the 5. Now I equate the two exponents, multiply both sides by 7, and I get 35 months. So this concludes the lesson on solving exponential equations. Hope that made sense for you. Thanks for watching. Have a great day.